Good morning, everyone. We'll take another minute or two and then get started. We'll take another minute and then we'll get started. All right, let's jump in. Thank you so much for joining us today. So today I want to talk to you about new pganalyze features that help you compare Postgres query plans and tune slow queries. I also want to give you some of the background on how and why we built these features to help you tune your Postgres databases better. So today we're going to talk about 7 different things. We'll start with a little bit of an overview of how we can identify slow queries in our Postgres database and their query plans at scale. At scale, meaning we're not just talking about an individual query, but we're essentially talking about how can we either, on a query with many different queries, identify the ones that are interesting to look at, or if we have many database servers that we're taking care of, how can we make sure that, in each of them we have a consistent way of addressing slow query performance. Then I'll talk to you and show you a new plan statistics feature in pganalyze that we're actually going to launch next week, but you are getting a sneak peek of how that's going to look like. Then I'm going to show you a new plan comparison feature in pganalyze. This is something that we currently have in early access, and I'll give you a few details also on how to join our early access program at the very end. Fourth, we'll talk a little bit about when we have a slow query, how do we debug why the query is slow? We'll give you a little bit of a background on that. If you've attended previous webinars where we talk about query tuning, this is essentially a lot of that same material, but simplified just in the context of how we can effectively use this within the context of the new pganalyze features. Then we'll focus on how we can benchmark alternate query plans. We'll talk a little bit about how we can use Postgres planner settings and how we can use hints with PG hint plan to influence which query plan gets chosen. And then last, I want to give you an overview of a new feature in pganalyze called query tuning workbooks. Query tuning workbooks are also in early access currently. And again, at the very end, I'll include some details on how you can join the early access program. Query tuning workbooks help you optimize slow queries by essentially making it easier to running, explain, analyze at scale for a particular query, testing different kinds of parameters and identifying why a query is sometimes slow, but not always. And at the very end, I'll hint at an upcoming feature that we're still working on called Query Tuning Advisor. I'll give you a little bit of a sense of where that will help you in the future, as well as answer any questions you might have about this or anything else that we talk about today. With that, let's jump in. So I want to give you an overview first of how we can identify slow queries in our Postgres database and their plans. So generally, I ask myself this question, maybe coming from, why is my database so slow because I'm spending so much IO time or CPU time? Or maybe I'm coming at this from, having heard an application engineer reporting that, the application is slow and we think the database is at fault. So what pganalyze does, and this is something we've done for many years now, is we give you an overview of all the queries that have run in the system, and we let you do a breakdown into what each of these queries has done over time. So this is not new, but this is it's essentially a very important feature. And we initially built this many years ago because we ourselves were running a Postgres database and we needed to optimize it. And this was, how we turned the kind of intransparent, here's a database using a certain number of CPU into an actual understanding of which query is causing the slowness in the system. Now, what pganalyze also has done for a couple of years now is we have an integration with the auto-explain extension in Postgres. So auto-explain lets you record from a particular query how that query is behaving at a particular point in time, at a particular execution. So the regular query statistics that we show as an aggregate, those are based on the pgset statements extension in Postgres. This don't tell you essentially, the real details of what's slow, but with auto explain, you can actually dig in and you can see exactly which part of the query is slow. Now, this is the same essentially as a text-based explain, right? So you can always go back in pganalyze to see the text-based version as well. And this really is just saying, which part of the query is doing the work. Now, you can also use this to identify whether a query is always slow or just sometimes. So here's an example where you see essentially the purple dots in pganalyze and the query stats graph. Those indicate these outlier executions with auto explain. And so the idea is that, I can dive in and I can click on these to essentially see the particular samples that were recorded. Now, in this example here, we see that the average time is 1.4 seconds, but the outlier execution cases were 14.6 seconds. So clearly, this is something that, is worth an investigation. Also, one of the things we've recently improved is the planned fingerprinting in pganalyze. So planned fingerprints, the idea is that a planned fingerprint shows you a change in plan structure. And this is something that Postgres itself does not do. This is something that pganalyze does when it looks at the plans, when it analyzes the plan data that we're getting, and we essentially look at the node types as well as significant attributes of the plan nodes, and we say, is this the same plan or is it a different plan? And so when you look at the explained plans in pganalyze, you can use that to identify whether the plan has changed. Now, here's an example where, we have essentially almost all the recorded executions here or recorded plan samples have this E14 plan fingerprint, but then one of them is an outlier. And then also that one was essentially one that was slower. Now, here's the first new feature that we're excited to announce today. So plan statistics in pganalyze is a new functionality that we're officially launching next week. You're just getting a preview today. And so we started this by essentially saying, this is essentially very simple, which is we're just giving you an improved view of all the samples that we already collect. So this is something that you have available today for all databases in pganalyze. This just makes it easier to understand, am I seeing 20 different plans or am I seeing, the same plan always? Now, the really exciting thing is when we're digging into documentation for Amazon Aurora early this year, and this today is an Amazon Aurora specific feature, but we have plans to broaden this to other database providers as well in the future. So Aurora introduced what's called Aurora stat plans. And at pganalyze, we have customers across, different providers. So people use GCP, people use Azure, but we do have a substantial number of customers on Amazon Aurora. And so we decided that based on Aurora enabling this new Aurora stat plans functionality to build this into pganalyze right away. So the idea is that Aurora stat plans essentially complements what pgstat statements is doing and lets you track execution plans. This is also complementary to auto explain. So we actually think that this serves a different role than what auto explain does, because what this here does essentially lets us know, are there different plans or is it the same plan? And we'll come back to how we then use this in comparison, right? Because we might want to compare, has the plan structure changed or not? And so the new feature that, again, we're going to announce next week officially is we now have an integration with the new Aurora stat plans functionality. So you can actually see that here, in this case, on the plan samples view or the plan statistics view, I can see how for this particular plan it has behaved over time. Now, this is most interesting when there's different plans. So here, for example, is an extreme example where I have lots of different plans and they all have slightly different runtimes, right? So the middle one here, for example, takes 41 milliseconds. The other ones are a lot faster, right? And so the idea is that with this new functionality, this essentially is the best way to validate whether you're sometimes seeing a plan fall over based on certain input parameters. Again, to start with, this is going to be available only on Amazon Aurora when you use pganalyze together with Aurora. But we have plans to essentially improve on an existing open source extension, which we'll talk more about in the future, where you can run this on your own database servers or on other providers. Now, that's it with the Aurora specific things. Everything else here, is available to every database that we integrate with. So let's say, I've identified two different plans and I want to understand what has changed between these two plans. So one of the major new features we have now in pganalyze is plan comparison. So plan comparison right now is still in early access, but as mentioned, we'd be happy to invite you to that. So the idea is that if I look at an automated explain plan, this here is the auto explain data again. I might want to know what's different between the first and the second query plan, right? So this is that example we looked at earlier where we had one plan recorded as an outlier. Again, you can use this on any provider today. This is something that, uses the log-based approach for logging outlier executions. Now here, I can dive in and I can say, okay, for this first plan, which took 660 milliseconds, compared to the second plan, which took 6,000 milliseconds, right? It's about a 10x difference. Why are they different, right? Like, what is the difference between those plans? And so in the new plan comparison feature, what we now have available is essentially a way to select a plan A and select the plan B. And so what I can do here is I essentially choose that from my existing samples. I'll come back later to a way of doing this with a query of your choice. But to start with here, we're looking at the pre-recorded data that's already recorded in pganalyze. And so here I select, the bad case and the good case essentially. And so we do a couple of things here on the screen. So when we developed this feature, we initially started with looking at this more from a visualization perspective, but we actually felt that there might be an easier solution here just by using a text-based comparison, right? So what I found myself doing before, we kind of built this feature is I actually would go in and I would essentially take an explain text output and I would just keep removing things from the text until the explain plan looked simple enough, right? So essentially the text output was just, the major plan notes essentially. And then I opened that side by side in my editor and I would say, okay, the good case looks like this, the bad case looks like this. And so really just, simplifying text-based plan and then doing a diff on it actually is really helpful for understanding whether you are seeing two different plans and what's the difference. So in this particular example here, we see again on the left side plan A, that is the slow case, right side plan B, that's the fast case. And so you can see the red portions are essentially what is present in the bad case. The green portions are what's present only in the good case. And so we can see there is a structural difference, right? The left plan A, the slow plan, has a bitmap heap scan, a bitmap index scan. The right side has an index scan. But then more importantly, actually, the left side has a hash join with a hash and a sequential scan on one part of the join, versus the right side uses a nested loop. This is what's called a parameterized index scan on the right side. So essentially, the idea is that sometimes you can only use indexes if the index table being scanned is inside a nested loop. And so what we're seeing here is essentially that the good plan is correctly using a parameterized index scan versus the bad plan chooses to do a sequential scan. Now, we'll talk a little bit later about what that means and how we kind of, can reason about these problems. But really the big benefit here is that this is just a lot of work to look at manually, right? Like if you do this work yourself, you end up spending probably, I would say, half an hour with just, like running explains and like looking at, the differences. And so we just cut down on that debugging time here significantly just by showing you that structural difference. Now, what you can see on the right side is the other metrics of these plan nodes. And you'll see that if the plan has the same plan nodes, right? So for example, the aggregate part of the plan, that's essentially the same, right? Or the function scan is the same. And so I can see the difference there essentially just in the runtime. So for example, if you look at that fourth row where it says function scan, the function scan on the fast plan is actually slower than the function scan on the slow plan. So plan A has 74 milliseconds of runtime on function scan. The plan B has 480 milliseconds runtime on the function scan, right? So just that part of the plan is actually behaving kind of to inverse to the total runtime. And so this helps me understand, should I look at, the performance of that part of the plan or not? And the answer is no, right? Like that's not the part that's relevant. I can just basically ignore it, right? Because really what matters is, again, the hash join here in this particular case, which is where the problem sits at. Now, I can also pick different metrics here. So for example, one metric I find really useful is looking at rows. Rows are, of course, interesting in terms of how many rows does a query return, but rows are also interesting when you think about it, which part of the plan kind of works with how much data, right? So here's a good example of the sequential scan. So if you do a sequential scan and you're joining the result of the sequential scan with something else and you're not really limiting it, right? You're basically loading the full table, in this case, 5 million rows, in order to then, kind of do that join and remove most of them again, presumably. And so this, very clearly shows, even though this whole query returns a single row, at some point in time, the Postgres executor actually had to work with 5 million rows, right? And so that's really the idea behind showing these metrics here, is that we can now say, okay, well, clearly, if there was a part of the plan where so many rows were being worked with, that is something worth looking at. Interestingly enough, the function scan that we saw on the plan B here, right, that actually is quite intensive on the plan B, right? So like the 340,000 rows there, that is much more than the plan A. And presumably part of the reason why Postgres essentially chooses a different plan is because some of that data is differently shaped, right? So essentially these are two different cases, two different kind of objects we're looking at. One of them has more rows returned in the function scan. The other one has probably some statistics that then cause it to do a sequential scan. Now, what I can also do in this comparison here on the right side is I can see the index usage. And you can actually see the index usage here. So plan A, the slow plan, is not using one of the indexes, right? So that's really the one where we have that sequential scan, right? So that index schema, index metadata index, that one is only being used on the good plan, essentially. So I can see that very clearly here. I can also click on individual nodes in the plan tree on the left to see more details. So for example, I can click on the sequential scan and I can see information about what is the sequential scan actually doing. Was it, discarding all the rows right away? Or like here, I mean, this is kind of the extreme example because there's no filter condition on this either, right? Like this is basically a sequential scan that loads all the data into memory and it keeps the data in memory until after the join is complete. Versus if we look at the index scan, for example, we can see the index scan here. Again, an index condition uses that parameterized index scan, and that's really efficient, essentially, by comparison. Now, the other thing we've done here in the plan comparison is we've actually split out when you have a CTE in a plan or an init plan, which are technically run separately in Postgres, right? They're really different planner invocations. We essentially split that out clearly here. So in this example here, you can see that there's two CTEs and one init plan. And init plan is essentially a fixed expression that essentially gets run once, and then the result is being used in the query one or more times. And so the idea here is that I can clearly see the different parts here of the plan. So I can see essentially that the CTE essentially was the same, right? But the main plan, that's where there was a difference here in that index only scan, and that append essentially being only in plan B. And so that's something that you can also now see very clearly here in the compare view. One thing that we've actually experienced so far, and when we've worked on this with early access customers, is that oftentimes it's worth trying, like in Postgres 12, there was a change in how CTEs are handled. So if you have a CTE, Postgres no longer considers that an optimization fence. And so that means Postgres might choose to essentially eliminate the two CTEs here and pull them up into the main plan. Now, it turns out sometimes that's not ideal. And so you can use the materialized keyword to change the query to essentially, force Postgres to materialize it and do it like this, which is, using separate CTEs. And we've actually found that in some of our early access customer testing, that some customers really benefited, like, I want to say 10x, 100x improvement, I think even in one case, just by using materialized and essentially forcing Postgres to work with the data differently. So this is something where the compare really comes in, and I'll come back later to how you can do that kind of testing. Now, we'll move on from compare now. For now, we'll come back to this. I want to give you a little bit more background on how we can actually use this effectively. So let's talk a little bit about how to debug why query is slow. And maybe also before I jump into this, if you have questions, feel free to put them in through the Zoom Q&A feature. We'll come to questions at the end, so feel free to queue them up, and I'll make sure to get to them all at the end. Or if we don't have the time, I'll send you a follow-up email with all the questions answered. So let's give some more background on, with the plan comparison functionality in our hands and the plan statistics feature in our hands, how do we actually use that effectively? So before that, I basically want to give you some background on how I think about optimizing slow queries. So if you've been in one of our webinars before, this should seem familiar. But I think it's very fitting here because we essentially developed some of the older webinar content, then developed this feature set, and so this really goes hand in hand. So you have a slow query, right? The slow query is slow. What the standard process would be is if you're benchmarking slow queries, if you're improving them, you do an explain analyze, right? So explain analyze in Postgres, that's really your core tool to do query benchmarking. Based on the results of the explain analyze, you could form a thesis on what to change, and then you try out the change. A change can be rewriting the query. A change can be turning off some settings. We'll talk more about that a bit later. Now, after I've identified, a faster way of like getting the query to be better, then I can make the change permanent. So oftentimes, when we try out changes, we might do things that don't really scale. An example would be we might use a query hint. Hints are not something that's recommended to be used in production. And so the hint is useful for debugging, but then you may end up rewriting the query or changing some statistics configuration to really get to the query improvement overall. Now, let's start a little bit about talking more about how we use explain analyze. And if you've used explain analyze before, this should seem familiar, but I do want to make sure everybody has a good understanding of what, that basic tool in Postgres gives you. So just a quick recap, explain without analyze gives you the plan that the Postgres planner chose, but it doesn't give you any actual statistics, right? So this is really, the simplest thing. You can always run this, but it doesn't really tell you what went wrong. It just tells you what the planner intends to do or what the executor will do. Explain analyze gives you the plan chosen plus the runtime statistics. Explain analyze buffers gives you the plan chosen, runtime statistics, and IO statistics. There's a couple of other settings that Postgres introduced recently in your releases, like the serialize option or the settings option. These help you essentially get closer, like settings, for example, tells you which settings are different than your standard settings, which definitely is useful to know. The serialize option, not shown here, serialize in Postgres 17 shows you the overhead of emitting the result. So one important thing to know, even if you do explain analyze buffers, it doesn't actually serialize the results. So it doesn't really produce the actual data that gets returned on a network. And so sometimes there are cases where this can be misleading. And so the new serialize option essentially helps you, especially when you return large result sets, to really validate how slow or fast that is. Now, just again, quick recap. If you run explain, right, like the simplest thing is you just put it in front of the query. We get a text output like this. If we do an explain analyze, we get, different text output with a bunch more data. And then if we do explain analyze buffers, we get the IO statistics, like buffers meaning how many pages were found in the Postgres shared buffer cache and how many pages had to be read from disk. You have to multiply these numbers by 8 kilobytes, or the size of the Postgres page that's configured, to really make sense of it. Now, based on this information, right? So if we look at something like this, well, now we can think about, is the sequential scan the right thing to do, right? So really, there's thinking to be done here, and so for me, I think a lot of the things how I've improved my own skills in query tuning is I've just seen more bad cases essentially, and now I recognize them, right? And so I think really this is really to me the core skill set here is like if you are a database engineer, data platform engineer, database administrator, who's tasked with optimizing queries, I think really the thing you should improve on, or you should essentially learn as much as you can on, is what bad plans exist out there and how we can identify them. So really this comes back to, though, right, like just to repeat this, is the planner's task is fuzzy, as Tom Lane said in the PGCon 11 session, where, basically it's not like there is the perfect plan. It's basically that there is a bunch of really similar plans often that, sometimes are better, sometimes are worse. And so it's not like the planner can say, always use this plan. And so really the responsibility of the planner is find a good query plan, don't spend too much time or memory finding it, and support the extensible aspects of Postgres like PG Vector, for example. And so this, especially the second part here, really gets us often because Postgres doesn't really exhaustively search for the best query plans, doesn't really do any data sampling, and then one of the things that I really hate about the Postgres planner is it will happily keep doing the wrong plan all over again, right? So essentially, even if Postgres has executed it badly one time, it will happily execute it badly the second time. There's no feedback mechanism essentially in core Postgres, and so again, right, like doesn't keep track of execution performance. It doesn't change the plans when the expectations don't hold true, right? So like if more rows are matching, all these things are essentially not something the planner is doing, which is really why we're here, right? Because we essentially have a suboptimal system that is in production that behaves in a certain way, and we need to tweak it sometimes to get the right result. One of the things we added a couple of months ago is a new insight in pganalyze for inefficient nested loops. So this is just an example of what you can, if you look at a query plan, again, this here is the visualized version in pganalyze, but you can see, for example, if you have a nested loop and the nested loop has a row count of 1 in the estimate, right? So the rows part, but then the actual rows, like the explain analyze part, says actual rows, for example, 1007. And so that means, nested loop returned a lot more rows than expected. Or what's also relevant here is essentially the outer side of the nested loop, like the part that controls how much data is being worked with. Like if there's a misestimate there, that can really drive bad query plans, because Postgres likes to use nested loops when there's very little data and likes to switch to a hash join or a merge join when there's more data, right? And so this can be a good insight, essentially. Like when you see this in pganalyze, it's a good indicator that you might want to compare the different plans and understand, which one is better, actually. And so, yeah, here, maybe just another example where we have, the individual estimates actually are correct, but then a nested loop essentially gets it wrong, right? So the other thing to note here is essentially Postgres doesn't have good statistics about when tables are being joined together, how many resulting rows there are. Like really joins can oftentimes lead to bad row misestimates. And so suppose, we formed a thesis, we'll talk a bit more about in a second, then it comes to trying out the change. And so this is really where we actually have to go in and, for example, try, a plan without a nested loop, try, a plan with a different index and such. So this to me is really the next part here, which is how do we, understand when a bad plan was chosen? Well, we start by forcing the good plan, right? So we essentially start to understand how did Postgres end up, using the bad plan? What's the cost estimate difference? So this to me is really the other core portion of the skill set, right? So it's like you go from forming a thesis to testing out the thesis by benchmarking it. And you really have, the two main things, well, three things we can do here is we can use settings, which I'll talk about first. We can use a hint, and we can also rewrite the query, right? So we can obviously, just change the query to work different. Now, simple example here, suppose we have, a query that's like select star from this table where a particular object ID is 1, 2, 3. We give this to the planner. The planner gives us the good plan. Always when there's a good plan, there's also a bad plan. The planner just didn't decide to use it because the cost on a good plan was lower, right? So here the cost on a good plan is 250, the cost on the bad plan is 300. So planner went with the good plan. Now, suppose I have a different query where the object ID is 456. I give that to the planner. Now the planner gives me the bad plan. Why does the planner give me the bad plan? It's because, well, the good plan was also being considered, but in this case, because of the internal statistics, the good plan actually had a higher cost, right? Because the good plan had a cost of 500, even though the good plan here has a lower runtime. That's at least the theory. The bad plan was chosen because the bad plan had a lower cost. And so it's really this mismatch between the cost estimate that the planner does and the runtime that actually happens at query execution that is causing us a problem. Now, the simplest thing you can do, and I'm sure if you've run through some production, you've done this many times, is if you have a bad plan and it involves a particular planner feature, you can turn off that planner feature. So an example would be if the bad plan is a sequential scan and the good plan is an index scan, well, you can just do set enable seq scan off. And then what Postgres does in the current released versions is it just makes this cost extremely large to make it very unlikely to be used. There's actually a change here in Postgres 18, which is the next year's Postgres release, where this is more explicitly considered as a disabled cost. So you have some better kind of handling of edge cases here. But the idea is that, I can use set enable seq scan. I use this on a connection basis. So I run this on my, pSQL or wherever I'm running my queries, and this only affects the current connection. So this is safe to do on production as long as you use dedicated connection. And you can essentially use this to say set enable seq scan off, rerun your query, and then you'll see what Postgres did, right, and what the cost was of the good plan. Now, obviously, there's lots of these, kind of settings here. For example, there's enable index scan, hash join, hash ag, all the good stuff, essentially. It helps to, basically look at what plan nodes your plan has. And then if you want to try, like, for example, one thing I've, like at the very bottom of the list here is enable memoize. When Postgres 14 came out and added the memoize feature, I had some interesting edge cases on one of our databases. And so I just did set enable memoize off to see how it would behave if memwise was turned off, right? So oftentimes looking at the plan, seeing the node, and then turning it off is a good way to test the difference. Now, once we have the good plan, then it's really worth looking at the individual plan nodes and figuring out which part of the plan is essentially causing the bad cost misestimate, right? Because ultimately, like these settings, I mean, whilst you can certainly, like you could run your production with enable sec scan off if you wanted to, but it's probably a really bad idea, right? Because there are queries where a sequential scan is totally legitimate. Like if you have a tiny table, like a 1 megabyte size table, sequential scans are good. If you're doing select star from table limit 1 without any filter clause, sequential scans are good, right? And so I really do not recommend turning any of these off on production on a system-wide basis, only turning them off on, per connection basis for testing. And so that's why we care about, figuring out what went wrong so we can like fix the root cause. So another thing we can do, for example, if we see a hash or merge join is being used and we want to have the nested loop plus parameterized index scan, which is actually the example we saw earlier in the compare, we can do a set enable merge join and set enable hash join off. That essentially forces a nested loop as the preferred join method. Now that said, this is kind of where the core Postgres debugging ends essentially. So the really frustrating thing essentially is if you have cases where you're interested in maybe just changing parts of query plan, Postgres itself today doesn't really have a built-in mechanism to do so. There's actually a current patch being discussed again for Postgres 18 to improve the facilities here upstream so that extensions like PG hint plan, which we're going to talk about in a moment, have a better way of hooking into this and influencing the planner. But today, unfortunately, Postgres itself on just standard Postgres really only has these settings as a way to control behavior. Now, PG hint plan, on the other hand, you can use today. I've used this many times, again, on production systems to debug plans. This is available in the cloud on all the major providers. And so when you enable PG hint plan, what it lets you do is lets you influence plan in a more kind of fine-grained way. So here in this example, I have a bad plan with a particular join order, like two tables being joined in the wrong order, essentially. Like schema column stats comes first and then schema tables. I know that there's a better plan available. Now, if I, for example, use the planner settings, I can set enable memwise off. I get the other plan with a better join order, right? This is just the coarse way that you can always do. Now, with PG hint plan, I can get extremely specific. So I can do something saying, I want this particular join order, and I want to use an index scan on this table with this index, and an index scan on the other table with that index, and also I want to turn that setting off, right? So that essentially enables me to have a lot of control over how the plan shape looks like. Now, PGN plan is really frustrating to write, I'll be honest with you. So I often find myself, like these hint comments are really difficult to get right. But when you do get them right, they really tell you the story, right? Because it gives you the cost number and it lets you ensure that you're actually getting like validating what Postgres might be able to do if you got it to use the right statistics, for example. Now, if we look at, here in this particular example, really it comes down to cost, right? So the good plan had a cost of 1.4 million. The bad plan without the memwise had a cost of 14 million. And the bad plan with the memwise had a cost of 970,000. And so really that's the reason why, the bad plan was chosen is because memwise in this particular example caused the bad plan to be cheaper than the good plan, right? Like the cost numbers were lower. And so that's why we were kind of getting the behavior that we didn't want. So again, it really comes down to the cost numbers because the planner always goes for a lower cost. Now, these kind of things actually, make a difference in production. So here, this was an actual change we made. This is, by now it's actually a couple of months old, but the difference here really is, we, in this particular case, we added a where condition, so we actually didn't end up, adding the hint in production. We just, were able to see that with an extra where condition, Postgres was also reliably using the right plan. And so that's really the motivation here often is saying, okay, well, clearly, Postgres is doing something bad. Let's rewrite the query, for example. Which brings me to the third new feature here that we're talking about today, which is query tuning. So query tuning or query tuning workbooks There's a new feature in pganalyze that lets you optimize queries, kind of like I just described with explain analyze, but do that in a way where you essentially can do this in pganalyze and you can share the results of your tuning exercises with other team members as well. So I'll give you an end-to-end example here. So let's say, for example, we have a trace of a slow web request. So I'm actually starting this not in pganalyze, but I'm starting this in our APM tool. So this is a screenshot of Honeycomb, which we internally use for pganalyze itself. Now Honeycomb just gets like slow request information. Now I go in here. In case you didn't know, we have an integration with OpenTelemetry, so we can actually get you the spans, like the explain plan information, into your OpenTelemetry systems like Honeycomb or other providers, like New Relic and such. And so I use this here to identify, okay, the problem actually is a slow query, right? Like we actually have a problem here with the database side, not the application side. Now I have this query plan of 7 seconds here. I dig into essentially like here, I had a link here to the pganalyze plan. So I go through to that, I see the visualization, and I kind of come back to this, nested loop problem, right? So this is essentially the case we mentioned earlier, where I kind of, have multiple misestimates of nested loops. And so I'm trying to understand, what can I do about making this differently? What can I, how can I improve this? It also takes a lot of time, right? So the index scan there essentially takes 99% of the I/O time. And so with the new query tuning functionality, what you can do is there's essentially a new trigger that you can use to start a workbook. So the idea is, like all the data we're looked at so far for this query, that's automatically collected, right? So the explain plans and such, I have that automatically, but that really just tells me what the system is doing right now. It doesn't really tell me what's possible. And so what we found is that we ourselves, when we're tuning our database, we would, go out of pganalyze essentially and work with, VS Code or GitHub Gist or other ways of organizing like a spreadsheet, just to organize our experiments. And so really the idea behind the workbooks is that when you're going into this experience of trying alternate plans, you can now do this right in pganalyze. So I click Tune Query and Workbook. I choose a particular name and description for that workbook. And then one of the things that pganalyze does is it automatically names the parameters that are referenced in the query. So pganalyze, when you have a query in pganalyze, it always works with a normalized version of the query because we group multiple executions together, right? Now, commonly, we show this to you with the way how it's represented on the Postgres side and how the application side sends it when it's using bind parameters, which is you have a $1, $2, $3, and such. One thing I've learned when I tune queries is that it's actually really frustrating when you're rewriting a query and you, like, for example, here we have, at the top, we have the CTE with total times, right? And so one thing I like to do is I like to sometimes just run parts of the query to validate how fast or slow is this section. And if I, if I want to just tune a particular part, maybe I only focus on one part of the query. Or maybe I remove a where condition or add a where condition. And so what's really frustrating, and this might seem like a small detail, but it's actually really, takes a lot of time, is when you do these rewrites, you end up with essentially a lot of, stale numbered references, right? So you might remove something like it says database ID equals $1, $1, and you remove that reference, and then Postgres will complain, and Postgres will say, well, what was that $1? Like, I don't know the value. And so this was one of the things that actually took a good amount of engineering time, I would say, but is actually an important detail to this experience here, which is we turn the input query that you give us, we make it normalized with the numbered parameters, and then we give each of these numbered parameters a name. And the name is automatically inferred from whatever is next to that particular parameter reference. So we can see here, database ID equals $database ID. That's because you're doing a quality comparison on database ID. The other case, you're doing a between add, so it's named like the column that you're referencing. In some cases, we don't get that right. So, for example, later in this query, you can see param 10. That's essentially the generic way of referencing it if we can't identify how the query parameter is named. But you can also not shown the screenshot, but you can also change these names. So the idea is that if I know, for example, looks like O dot last is really the param 10, so I could rename $param 10 to last to make that easier. Now, the reason this matters is because one of the things we do here in this query tuning workbooks is we let you paste different examples of the query or give different parameters. And so the idea is, for example, here I'm picking this from the existing query samples. So the idea is you might query something for, in this case, there's like query ID and there's 3 different query IDs. and the query might behave differently. You might be getting different plans. And so core to this query tuning workbook experience is that we are testing different different input parameters, and showing you the plans for each of the different input parameters. And so then when you're changing the query, when you're rewriting the query, you can essentially validate that all of the parameters that you're testing are performing good, right? Because sometimes when I make changes like this, what might happen is that I improve the one case that's bad, but then with the improved query, like with the rewrite, for example, I actually break the other case, right? And we typically on the application side, you don't want to have an if condition that says, if customer one do this query, if customer two do this other query. Like that's really not what you want to do. And so you need a way to write the query effectively for all different kinds of input parameters. And so that's really why we thought that, it's really important in this, workbook experience that we make parameters a first-class citizen, and we actually bring it first and foremost in this testing. So I go in, I have my query, I have the parameters. I, either input them from an existing query I have, input them from the query samples that pganalyze records, or I can also input them manually by essentially just giving us the values in the query tuning workbook. And so then what pganalyze does is it either in a feature that is available in early access lets you run this automatically for the collector. I'm not going to talk a lot about that today because I don't have the full example here. But just to be clear, you can do this manually, which is the standard way of doing this. Or if you opt into it, you can also run this through the collector. So essentially, you don't have to do this work here of copy and pasting results if you don't want to. But the idea is we essentially run explain. You can see the command we essentially ask you to run, or that gets automatically run based on your choice, is explain analyze verbose buffers format JSON. We talked about analyze buffers earlier. Verbose just gives you a bit more information about how the data flows essentially in each part of the plan node. And then format JSON is just it's easier to parse JSON than text. Like it's more accurate, so to say. That said, we actually do support parsing text as well. So if you find yourself, only having text format, we actually have a pretty good text to JSON conversion for explain plan outputs internally. And so this here essentially, like you run this on your database, you paste in the output, and then what it gives you is essentially a comparison where you can click on the individual plans. So each of these plans here, I can click through, I can see, the visualization of the plan. So in one benefit here already in the workbook is that I can use this to essentially say, how has the query, performed like what are the issues, what are the explain insights? All of that is available essentially for queries of your choice. Now, so you don't have to only, do this with queries that you've run on your database previously. You could also come up with new queries and put them into the workbook and essentially get pganalyze's recommendations. Now, what I can also do here is I can do comparisons. So the full comparison feature we talked about earlier is also available here. And so this is very useful. Again, when I have, 3 different input parameters and I got different plans for each of them, with the comparison feature, I can essentially go in and I can see, okay, this part of the query is the problem. All right. The other thing, worth noting here, and I don't have a screenshot of this yet because we're still working on that feature, is it does help you understand different join order as well, just by looking at the different plan shapes. And so one thing I might want to do, let's say I have 2 examples. In this case, I just looked at the text version. And it's a bit hard to read here, especially in webinar, but essentially the top here uses the same index in both cases. Like the first part nested loop is the same, but then the second part on the top one essentially first joins on this query occurrences table, versus the second example joins on the query fingerprints first. This might seem like a minute difference, but it does actually make a big difference in terms of performance. Here in this case, the actual time on the bottom one was 2.6 milliseconds. The actual time on the top one was 428 milliseconds. And so that's really the differences that we might see is if join order is different, you might actually see very different runtime behavior. And so one of the things that the query tuning workbooks let us do is they let us create variants to test hypotheses. This is something that today, in the current version of this, this is something that you essentially have to come up with. So it's kind of geared more towards the expert users, I would say. But it is something that, first of all, in early access, we give you some input on this. So when you give us a slow query, we'll do the human work to essentially work with you in a screen sharing session and optimize a query with you to test our hypothesis of how the system works. Also, in an upcoming version, I'll talk about that in a moment, we're planning to give you an advisor to essentially give you these hints or ideas on what to try. So really, this is where, a lot of the knowledge comes in. Is like, in this case, okay, I want to try a different join order. That's, not accessible to a lot of people. And our goal is to ultimately make that accessible to a much broader audience, including application engineers. So in this case here, I'm trying a different join order. I'm adding this hint, right? So in the middle where it says variant query, I'm adding that hint that essentially changes the join order. And then I'm using that to like test different variants. So here, I've already done the explain analyze, or the collector has done it for me. I can now, see that, for example, in this case here in the baseline, there were kind of slower cases. And then for example, here I re-entered warm cache, that was faster, and then it was validating if I always use a particular index, how did it behave? You can see that in this case actually it was worse, right? But the idea really is that this lets you iterate on the different cases, right? So I can essentially keep changing this, keep running it until I find essentially the best possible execution, and then I can use that to essentially share with the rest of my team the outcome of my work, right? So I can essentially go and say, here's the investigation I've done. Here's the the optimized query that you should use based on this investigation. Now, maybe just to summarize, what are the things that we can use here? And some of these are things that we've gone into more detail on in a past webinar. So if you are like, this, sounds really complicated, I'm not sure what it means. In the follow-up email to the webinar, we'll actually include your reference to our previous webinar where we went into a lot more details on some of these aspects, including statistics and such. But the idea is things that I would try if I want to influence Postgres. So if I'm getting bad costs, I might try doing create statistics and analyze if I have like functional dependencies in my query. That is usually something I don't do as the initial debugging step. That's more later in the process, I would say. But it does really help a lot to essentially improve on bad plans for certain cases. If I have problems with join selectivity, right? So if I'm getting, like for example, earlier we had the example where there was a nested loop versus a hash join. Basically, that's a function of how much samples Postgres has for kind of the most common value lists. And so one of the ways of influencing this is increasing statistics target. Although I'll be honest with you, oftentimes join selectivity is just really hard to improve on. Sometimes it makes sense to review cost settings. So one of the things that, to be honest, still surprises me is that if you provision a new database in the cloud, basically all cloud providers give you random page cost as a default setting. Random page cost is how expensive it is to load data from an SSD or from a regular drive. And so the problem essentially is that the Postgres default of random page cost 4 is quite high, and it's not really reasonable these days. It does change your plans a lot if you change this. So probably the reason the cloud providers haven't changed this is because even though all of them use SSDs, although network, but still SSDs, the problem really is that, if you change this, suddenly plans change and people might be frustrated. But certainly if, you haven't changed this in your system yet, it might be worth testing random page cost changes. This is, something you could also test on a per query basis with the set random page cost on a connection. And so one of the ways you could validate this is use the new query tuning workbook feature in pganalyze to, say, here are my most important queries. Let me, change random page cost to 1.1 and rerun all these queries and confirm they're still fast, right? Like confirm they haven't changed the plans. Now, sometimes it makes sense to create multi-column indexes that align with certain biases the planner has. We didn't talk much about this today, just in interest of time. But for example, one of the things that the planner likes to do is do a bounded sort, which is essentially an order by limit that goes wrong. And so sometimes you can coerce Postgres into doing the right thing by creating an index that essentially looks like Postgres wants to use it. And so then Postgres does what you want it to do. Other ways of doing this can sometimes be to, adjust the query slightly. Order by limit, there's a infamous trick with adding a +0 to an order by column to make work for that. And then fifth, if you have really complex queries with surprising join order, like we've seen this a little bit in our early access program, what I've found useful twice now in these conversations is to use materialized. So this is what I was referring to earlier. If you essentially have a query where a query might be simple. It might be, select this from this table, join this other table, join this other table, join this other table. But then you're somehow getting odd behavior, like you're just getting a a big cascade of nested loops or something, and you're essentially saying, well, that doesn't really make sense. Like, why is Postgres doing so many nested loops? And so one of the things that I found useful is essentially using materialize to intentionally combine data in a certain way. So really force, Postgres to join this table, join that table, then have the results set in memory, and then afterwards join the other tables. And so that can be really useful as a rewrite. And again, with the query tuning workbooks, you can actually, change the query and record kind of your experiment with changing the query. And then last, if you have a multi-tenant app, what I've actually found useful is adding explicit clauses. So for example, suppose you have a, I don't know, CRM tool, and each of your customers, has their customer ID, right? And like, they have their own like contacts in each of their CRM accounts. Yet, when you're querying, you might be querying just by contact ID instead of customer ID. Now, it can sometimes be helpful to essentially, if you're joining multiple tables, to essentially make sure that you have this customer ID, available on each table and indexed on each table, and then you're just adding, where table one customer ID equals 1 to 3, where table 2 equals customer ID 1 to 3, even though you're joining them together, you're essentially allowing Postgres to use different join methods. And so this can actually be make quite a difference. So something worth testing if you have that kind of schema. And then last, I want to hint just a little bit at what we're thinking of with Query Tuning Advisor. So whilst we have some mockups on this, I don't have them ready to share today. So I'll just hint you a little bit of what we're thinking with Query Tuning Advisor. So the general idea is that, what we have today with the query tuning workbooks and applying comparisons, that essentially makes the human part of this activity a lot easier. So really, this was developed, all the functionality I showed you today was developed out of, ourselves running into these challenges and just, finding us doing a lot of manual work. And so this makes the manual work a lot easier. What Query Tuning Advisor intends to do is, in some parts at least, identify common cases and tell you about them ahead of time, right? So you don't necessarily have to go into a tuning workbook. It can actually notify you when something pathological is detected. And then if you are in a workbook and you're tuning a query and we see something odd and we have an idea on what to try, right? Like maybe you should try a different join order. Our idea essentially is that we can tell you exactly what to try. And then once you've tried it, also, like give you an easy solution essentially that you can share with the team. So really, this is intended to be the superpower of the database engineer or even the application engineer to be able to identify what part of the query is slow. Just to give you a sense for the cases we're thinking of to handle in this advisor. So I talked about earlier, when like inefficient nested loops are happening, nested loops where rows are not one, that's one of the cases we're looking at. We've seen some cases where group by is causing wrong index usage and to do, the sort order. And so, one of the things the advisor intends to do is essentially give you, enable you to more easily try alternate indexes and confirm that there is actually a better index available. There's this really famous pathological case of order by limit due to how Postgres likes to do its quick start scans. So that's something that we also intend to cover here. And then there are a few other things we're looking at. We're not sure yet if they, will be in the initial release or not. But we're looking at kind of, functional dependencies causing wrong index usage, JSON-B expressions causing wrong index usage. Sometimes you have a bitmap heap scan turn lossy, which means it essentially does a lot more table access. And so you might want to force it to do an index scan instead. And last but not least, there's sometimes cases where kind of large result sets cause certain misestimates. And then, as mentioned, we have some cases with MemoWise also that we know about. This is not a comprehensive list, right? But our idea essentially is that we build on a repository of known bad cases. And with the query tuning advisor, our idea is that we have this automatically detecting those cases for you and telling you what to do to improve them. That said, if you're interested in learning more about the workbooks or about the advisor, we have an early access program currently. Just to summarize this again, so the planned statistics feature I showed you, which is mainly like on Aurora, that's really I think an amazing new addition. That one is actually officially launching next week. But for the query tuning workbooks, like where pganalyze can help you run, explain, analyze on the query and tune the query iteratively, and for the plain comparisons, those are things that will launch officially in a couple of weeks. But if you are interested in getting access now, we currently have this open to current cloud customers. If you're not currently a customer, definitely feel free to talk to us as well. We'd be happy to give you an in-person demo. But if you want to participate in the early access program, we really are focusing on somebody who has pganalyze integrated with the database server, with their production database server. And then what we're doing is we're doing one-on-one sessions where we go together on a call and we essentially spend 60 minutes tuning one of your queries. So this is free, like you're not paying anything for essentially a consulting hour in a sense. But our goal is that, you go in, you test the experience, kind of have a slow query. We run explain analyze with the new query tuning workbooks feature with you screen sharing. And then you'll also get access to this for the rest of your team. So essentially, once we've given you the introduction to the feature, you can also use this to kind of share this in the team and do this work going forward. And then this feedback is also what we use in the process of developing Query Tuning Advisor. So our goal essentially is to see more bad cases, right? So bring us your bad query plans. We're really interested in seeing more of these cases so we can incorporate them into Query Tuning Advisor. If you're interested in joining the early access program, the post webinar survey has a question on that. So feel free to, essentially express your interest there, or send us an email as well. And then we'll get back to you with next steps in that. And that's really all I had today. There's definitely a lot more we could talk about, but I want to make sure that we stay within the time allotted. And we do have some more time for questions. If you have more questions, please use the Q&A feature in Zoom, and I'd be happy to get to them. I'll spend maybe 5-10 minutes answering questions, and then anything else we'll get to asynchronously. You'll also get an email with a recording of this webinar tomorrow around the same time. And then let me take a sip of coffee, and then I'll look at the questions. All right. So Ivan had a question on, we talked about auto-explain in the very beginning. Can auto-explain safely be enabled in production, or does it add overhead to the query execution time? So just to reference again, auto-explain, that's the extension in Postgres that's built into Postgres that lets you record slow executions in the logs that pganalyze can pick up. The quick answer is that it is safe to enable in production with the right settings. There are some edge cases where it can be noticeable overhead. In our experience, though, it is something like in our documentation, we have very particular settings like log timing off, log analyze on. So if you follow these instructions, our general guideline is across the board less than 1% overhead. There are some cases if you turn on all the settings, with the most expensive being log timing. Other people have reported around the 3% overhead. But those are really, I would say, more the edge cases. And again, that's not what we recommend for production. So I would say, in my experience, let's say 1% performance hit across the board is worth it because you're just getting so much more information about what happened in the bad cases. But certainly worth thinking about and making a decision. And then Martin had a question on, let's see if I got that right, whether a planned fingerprint will always reference the same query ID. Good question. So let's take a look at that. Let's see if we can go back here. So should really have a better table of contents there, I suppose. All right, so we go here. Okay, so the question was, will a planned fingerprint always reference the same query ID? And so first of all, when we say query ID, well, it's maybe important to clarify terminology here. So in pganalyze itself, there is a query fingerprint and there is a planned fingerprint. Both of these are calculated by pganalyze. So that means that the fingerprint here, just for context, both on the plan and the query, they're actually the same across different servers. So if you have two Postgres servers, they will, and the query structure is the same, or the plan structure is the same, they will have matching fingerprints. Certainly, theoretically, you could have two different queries have the same plan fingerprint, right? So if the plan shape is the same, but for example, one of the maybe a good example is like one of them has another query in the target list, or another value in the target list, so it returns a little bit more data. It could be that the plan fingerprints are the same across two different queries. Now, separately from that, there's also the Postgres concept, as well as the Aurora concept, for example. So Aurora Stat Plans has this plan ID and Postgres itself has a query ID. Those behave very similar. So a query ID, a given plan ID could recur across multiple query IDs. It's unlikely, but it could happen. And so you really do have to think about these together. We do also, just for context, by the way, give you the original plan ID here in the UI for Aurora, because with Aurora Query Plan Management, you can use the plan ID to essentially force particular plans. So that's something very Aurora specific, but it's something we added here for that particular use case. And then let me see. Martin had another question on be nice to use different work mem settings for transaction or user. Can pganalyze help to find better values? So kind of going back to how we think about optimizing maybe this loop here, right? So workmem, for example, is interesting because workmem, in my experience, actually, so workmem is important because workmem says how much memory does the executor use, right? So like how much memory, like is it allowed to essentially do a sort in memory versus does it have to sort have to spill disk, or is it hash join being used, certain kinds of things. So today in pganalyze, we have some workmem recommendations. They're system-wide. They're not really useful for this kind of debugging. With the query tuning advisor, we are considering adding workmem as one of the things we consider. So for example, when we see, pathological example would be you see a sort spilling to disk, or you see a hash join with multiple batches. That could be an example of, where more workmem would be good. And so the thinking is for the advisor is it would give you something like, set workmem to a higher value, validate that the query plan improves, and then think about changing workmem more permanently, right? Certainly you could actually set the workmem on a per query basis. It just gets a bit tedious to manage, but that technically is also, per connection or per query settable. So I would say, yes, pganalyze can help you with this. Today, it can already do this on a system-wide basis. And then with some of the new features in the context of query tuning, we can certainly also do that as well. Let me see if I can. A few more questions. If there's more questions, definitely, please bring them up. Yeah, so let me see if I got this right. So John had a question on kind of the biggest issue being identifying the problem. So I think in this, if I read John's question right, or John's note right, the biggest challenge when doing this kind of work is essentially forming a thesis on what to change, right? And then the other part that's really challenging is actually getting this into production, right? So John gives the example of PG hint plan, noting that PG hint plan is can be very tedious to work with, which I would definitely agree with. And so the way that pganalyze helps you here, I would say, is first of all, so I think this work is happening today, but only some people know how to do this. And so I think one of our first goals here is to essentially make this more of a standard approach, which is kind of the loop we're showing here, which is the query is slow, figure out what's bad, and then improve it. Now, thinking ahead though to the query tuning advisor work, really where it comes back to, maybe I should accelerate here a little bit. So suppose we're in a situation like this where we found a variant, the variant is better. Now what do we do, right? So it kind of comes back to me to how do we guide the planner? I think there's a short-term way of doing it, right? So like hint plan is really the way of saying, okay, now hint plan proves that there's a better plan. And then it's a question of identifying, well, how this particular part of the plan can be influenced. And so really our intent here with these upcoming features on the advisor side is that we actually want to make that very clear to you. Like if we see that there's, for example, a cost misestimate or row misestimate rather, then, and we know that, for example, there's no create statistics, then we can, hint to you and say, well, have you tried create statistics, right? So sometimes even just noting or suggesting, some of these more, advanced Postgres features can make the difference here. I do not recommend using hint plan to force something in production. As mentioned on Aurora, there's Aurora plan management, but it's really also similar in a sense to hint plan, right? So it's really kind of tricking the Postgres planner into behaving differently. And so in my experience, really ultimately what you should try to get to is make one of these changes listed here, which are more stable, I would say, than using a planner hint or some other way of forcing a plan. And then I think I have two more questions. Let's see if we can get to those. So let's see if I can get to Dave's question here. Let's see. Um, so I think Dave notes saying a table scan with filter predicate might be costed slightly less than index scan. Yeah, so I think essentially the argument I think that Dave has is kind of the case we were looking at here earlier. Um, let's see. So I think if I got the question right, it's kind of like a situation like this, right? So actually this one here. So essentially when there's two very similar plans, but then one of the plans actually has really catastrophic behavior, and essentially like it's not just essentially maybe necessarily individual execution, but it's really saying, the overall risk, right? So like how bad is it? Like if the planner got an estimate wrong, how could we essentially make sure that we don't choose risky plans? And so this is actually something, just thinking about this from a Postgres upstream perspective, right? So in the Postgres community, it is certainly being discussed, to like, I think people like there's definitely lots of different opinions on how the planner should work. But one of the things, that I do see being discussed is essentially people saying, well, really the problem is that, sometimes the plan is slightly better, but the I think, Dave, that's what you're also getting at is there are situations where even, a slight misestimate suddenly leads to a catastrophic plan. And so I do think that, the role that we, as PG analysts have here is more, seeing these cases and maybe, in some cases bringing them upstream to the community. But I do think that, in terms of risky plan choices, that's ultimately a Postgres planner problem, so to say. And so I think we, as a user, the things that you have control over ultimately would be, again, create statistics or other ways of essentially making sure that Postgres is just making a larger cost difference, right? So what you're ultimately trying to do is get Postgres to not have very similar costs, where one plan is extremely bad and one plan is good. So I would say, in practice, all of what we discussed today applies. But just from, how Postgres thinks about risky plans, I think that is being discussed. I don't see there a lot of significant progress necessarily, but I do think that there's, at least a premise in terms of people understanding this problem better than they have previously. Um, and then I think Michael just had another short question. This was actually talking about a feature we didn't talk much about today, which was the index advisor. So just for reference, pganalyze has an index advisor feature. And I think Michael asks about, does it have, I suppose actually index advisor, I guess it was more like partitioning. Okay, so I think the question was, how is there an advisor in pganalyze that helps you assess the different table partition strategies? So not really something we talked about today much. I think the quick answer to that is not really today. So I think today pganalyze doesn't make partitioning recommendations. It's something we are looking at. But I would say today, for example, we discussed here, this is really more of you have a given schema, and within that schema, how can you tune the query? So that's really kind of what we're focused on with this current work. But yeah, I think that was all for today. Thank you so much for joining. As mentioned again, if you're interested in the post-webinar survey, please let us know if you're interested in early access, and really appreciate you joining us today. Thank you and have a good rest of your day.